Welcome to video 3. Last time we built a bigram model that looked at a single character of context. And the names it produced were pretty rough. Today we fix its biggest weakness by giving it more context. Using a multi-layer perceptron. Following the classic 2003 paper by Bengio and colleagues. Here's the plan. We'll feed the model the last few characters instead of just one. We'll embed each character into a small learned vector. We'll push those through a hidden layer with a tanh nonlinearity. And we'll predict the next character with a softmax. The loss in the training loop are exactly the ones you already know. Chapter 1. Why we can't simply count longer context. You might think, just count triples, or longer sequences. The problem is the table size. One character of context needs 27 rows. 3 characters needs 27 cubed. Almost 20,000. 5 characters is already 14 million. 10 characters would need 200 trillion rows. And almost every one of them would be empty. Counting simply doesn't scale. A neural network sidesteps this entirely. Instead of enumerating every possible context, it learns a compact representation. Chapter 2. Building the dataset with a sliding window. We pick a context length, called the block size. Let's use 3. So we always look at 3 characters and try to predict the next one. We slide this window across each name, padding the start with the dot token. For the name Emma, the examples look like this. ... predicts E. ... E predicts M. EM predicts M. EMM predicts A. And MMA predicts the end token. Each row is one training example. 3 input characters. 1 target. Chapter 3. Turning characters into learned vectors. The first part of the network is an embedding table, called C. It has 1 row per character. And each row is a short vector of learnable numbers. Say 2 or 10 dimensions. Looking up a character just means grabbing its row. These vectors start random, but training will arrange them so that similar characters get similar vectors. To embed our 3 context characters, we look up all 3 rows and stack them together into one input vector for the network. Chapter 4. The shape of the network. Now the full network. We take the 3 context characters and look each one up in C. Giving 3 vectors, we concatenate them into a single input vector. That goes into a hidden layer. Multiply by a weight matrix W1. Add a bias. And squash with tanh. The hidden activations then go through a second layer. W2 and B2. Producing 27 output scores. The logits. And softmax turns those into probabilities. It is just embeddings. One hidden layer. And an output layer. Chapter 5. Following the tensor shapes through the network. Let's trace the shapes. Because in deep learning, shapes are everything. X is a batch of examples. Each 3 character indices. We index into C to get embeddings. Batch. By 3. By embedding size. We flatten the 3 vectors into one long row per example. That goes through the first layer and tanh. Giving the hidden activations, batch by 200, and the second layer produces the logits, batch by 27, 1 score per possible next character. The whole batch flows through at once, in parallel. Chapter 6. Why we need a nonlinearity at all. Here's a subtle but crucial point. If the hidden layer were just a matrix multiply with no tanh, then 2 linear layers in a row would be equivalent to a single linear layer. X times W1 times W2 is just X times some combined matrix W prime. No matter how many linear layers you stack, you get back something linear. No more powerful than the Big RAM model. The tan H is what breaks that collapse. By bending the space between the layers, it makes the network genuinely nonlinear. And that is what gives it the power to learn complex patterns that a simple linear model never could. Chapter 7. How big is this network, really? Let's count the parameters. The embedding table C is 27 by 10. 270 numbers. The first weight matrix W1 is 30 by 200. 6000. Plus 200 biases. The second layer W2 is 200 by 27. 5400. Plus 27 biases. Altogether, about 12,000 parameters. Compare that to the 200 trillion rows a 10-character count table would need. The network captures rich context with a tiny fraction of the memory. Chapter 5. The loss, done the numerically stable way. The loss is the same average negative log likelihood as before. We could write it by hand. Exponentiate the logits. Normalize. Then take the negative log probability of the correct character. But in practice we call cross entropy directly. It does the same math in a single fused, numerically stable operation. It subtracts the max logit first to avoid the exponentials overflowing. And it has a simpler, faster backward pass. Always prefer it over rolling your own softmax. Chapter 6. Training fast with mini batches. There are around 200,000 examples. Computing the gradient over all of them every single step is slow. Instead we grab a small random mini batch. Say 32 examples. Each step, the gradient on a mini batch is noisier. An approximation, but it's good enough in direction. And we get to take far more steps per second. It's much better to take many approximate steps than a few perfect ones. Chapter 7. How big should each step be? How big should each update step be? That's the learning rate. A great trick is to sweep it. Try many learning rates over a wide range and plot the resulting loss. If it's too low, learning crawls. If it's too high, the loss bounces around or blows up. Somewhere in between is a sweet spot. The lowest point of this valley. We pick a rate near there. A common recipe. Train most of the way at that good rate. Then decay it. Drop it by 10 times near the end. To settle into a good minimum. Chapter 8. Splitting the data to measure honestly. As the network grows, it can start to memorize the training names instead of learning general patterns. That's overfitting. To catch it, we split the data into 3 parts. About 80% for training. The weights, 10% as a dev or validation set. To tune choices like the network size and learning rate. And 10% as a test set, which we look at only once. At the very end, if training loss is low but dev loss is high, you are overfitting. Chapter 12. Seeing overfitting happen. Overfitting is easiest to understand by watching 2 curves. As training proceeds, the training loss, in green, keeps dropping, because the network is memorizing the training names. But the dev loss, in red, the loss on names it has never seen, falls for a while and then starts creeping back up. That growing gap between them is overfitting. The queuers are getting more data, using a smaller network, adding regularization, or simply stopping early. At the moment the dev loss is lowest. This is why we always watch the dev set, not the training loss. Chapter 9. A look inside the learned character space. Here's something wonderful. If we make the embedding two-dimensional and plot the characters after training, they organize themselves meaningfully. The network was never told what a vowel is. Yet a, E, I, O, and U drift together into their own cluster, because they play similar roles in predicting the next letter. The embedding learned structure about language on its own. Chapter 10. Making it bigger and better. With this architecture we have knobs to turn. The embedding size, the number of hidden neurons, the amount of training, the learning rate, turning them thoughtfully, while watching the Dev loss, pushes the loss down from the bigram's 2.45 to around 2.2. A clear, real improvement, and we're only getting started. Chapter 11. The names it dreams up now. Sampling works exactly as before. Feed the context, get a distribution, draw a character, slide the window, repeat, but with 3 characters of context and a real hidden layer. The output is dramatically better. These are not real names, but they absolutely could be. Compare that to the bigram model's gibberish. That improvement came purely from more context and a better model. Chapter 12. What we built, and what's next. Let's recap. We embedded characters into learnable vectors. We used a multi-layer perceptron to combine several characters of context. We trained it with cross-entropy, mini batches, and a tuned learning rate. And we used train, Dev, and test splits to stay honest about overfitting. Same overall template as the bigram model, just a much bigger brain in the middle. And the names improved a lot. Next time, we look inside the network while it trains, at the activations and gradients, and meet batch normalization, a trick that makes deep networks train far more reliably. See you there.